Hello, geometry folks. So we have finished the first two investigations in Unit 5, and we are going to start investigations 3 and 4 next. So what this video lesson is going to do for you, it's going to review some of the things that we've learned in old units and old investigations that we will be using in the upcoming investigations. So we're still working with circles, but we're going to need to use what we've learned about angles and triangles. So this is a readiness lesson to get us prepared for investigations 3 and 4. All right, so we're going to start with parallel lines cut by a transversal. So what we have here is two lines which are parallel. That means they run even with each other. They never get closer together. They never intersect. So these are the parallel lines. Sometimes you see that they're marked in the problem with these little matching arrows that show that they're running in the same direction. That means they're parallel. And this line that cuts across both of them is called the transversal. Transverse means to go across. So you can see when the transversal intersects these parallel lines, it forms a whole bunch of angles, right? So at this intersection, there are 4 angles formed. 1, 2, 3, and 4. I numbered them, okay? And then when the transversal comes down and intersects the other parallel line, it forms 4 more angles, which I've numbered 5, 6, 7, and 8. So there are some very handy patterns to notice in our angle measurements. And here's how this works. If angle 2, for example, measures 70 degrees, angle 3 is also going to be 70 degrees. Because angle 2 and angle 3 are what is called vertical angles. I know you've heard me say that's my favorite angle pair. Okay, I like vertical angles. Okay, they're always the angles opposite. 1 and 4 is also a vertical angle pair. Those are vertical to each other, right? Down here on the lower level, on the other intersection, angles 5 and 8 are vertical. And so is the pair of angles 6 and 7. Okay, so any pair of angles that are opposite each other in an intersection are vertical angles, and they have exactly the same measurement. Okay, so if angle 2 is 70, we also know that angle 6 measures 70 degrees. And the reason we know that is because angle 2 and angle 6 are what is called corresponding angles. And what that means is that angle 2 and angle 6 are the angles that are in the same position. They're just moved to a different parallel line. So picture you're up here at angle 2. If you move down, it's like going down an escalator in a mall, right? If you go down to the lower level, the angle that's in the same position as angle 2 is going to be angle 6, okay? If you started with angle 3 and you move down to the lower line, the angle that's in the same position as 3 would be angle 7, okay? And angle 1 and 5 are corresponding, and angles 4 and 8 are corresponding. All right. Now, if we know that angle 6 is 70 degrees, we also can tell that angle 5 is not 70 degrees. See how these are all acute angles? Look at angle 5. Angle 5 is obtuse. It's a much wider angle. But we know something else about angle 5 and 6. Together, angle 5 and angle 6 fill in the whole side of that line. They make 180 degrees. So if this is 70 degrees, angle 5 is 110 degrees. And angle 5 and 6 together form a supplementary pair. Sometimes it's called a linear pair because they fill in a straight line. Okay, so you'll see it written both ways. Okay. Now, if angle 5 is 110, Angle 4 is 110. And how do we know that? Angle 5 and angle 4 are what is called alternate interior angles. Okay, interior means inside. If you think of the parallel lines as walls or borders, angle 5 and angle 4 are both inside the walls, they're inside the borders, but they alternate. They are on different sides of that transversal. Angle 5 is on the left side, and angle 4 crosses over to the right side. So those are called alternate interior angles. All right. And the last one we're going to do is if angle 2 is 70 degrees, angle 7 all the way down here is also 70 degrees because those are called, can you guess? If the 5 and 4 are alternate interior because they cross the transversal inside the lines, angle 2 and 7 are called alternate exterior because they also cross the transversal. This one's on the left, this one's on the right, but they are outside of the parallel line, so they are exterior angles. Okay? So those are very useful things to know. And another thing to remember, you guys, when you have a situation like this, two parallels with a transversal, there's only two angle measurements. Every angle here is either 70 or 110. All of my acute angles are 70. All of my obtuse angles are going to be 110. Okay? So every one of these pairs of angles, you pick any two angles, they're either going to be equal to each other or they're going to add up to 180. Okay? So that's useful. All right, now another thing that we're going to be using are some things that we already learned about right triangles. And the first thing that we need to remember about right triangles is our favorite Pythagorean theorem. And the Pythagorean theorem says if you have a right triangle, that means it has a 90-degree angle, a right angle, then what you have in that triangle, the two straight sides are called the legs, and the diagonal slanted side that's opposite from the right angle, that is called the hypotenuse. I usually just write HYP, okay? And the Pythagorean theorem says if you know the length of two of the sides, you can figure out the third length because the leg length squared plus the other leg length squared is always equal to the hypotenuse squared. Okay, so that's written a squared plus b squared equals c squared, where a and b are both the legs and c is always the hypotenuse. Okay, whether you know the length or not, c is always the hypotenuse. That's important to remember. People mess that up sometimes. Okay, so what does that mean? Well, that means in this problem, for example, we know one of the legs is 6. We know one of the legs measures 8. We do not know how long the hypotenuse is, but we can use a squared plus b squared equals c squared. One of the legs is 6, 6 squared. The other leg is 8, 8 squared. And if we add them together, that is going to equal the hypotenuse squared. Okay, well, 6 squared is 36, 8 squared is 64. If I add them together, that's 100, and that is c squared. Remember, that's c squared. I want to know what c is. I only want the hypotenuse. I don't want the hypotenuse squared. So I square root it. And if I square root both sides, because it's an equation, what you do on one side, you do exactly the same. If I square root c squared to get c, I have to square root 100, and that is 10. Okay, so my hypotenuse is 10 when my legs are 6 and 8. Now, sometimes, you guys, it's not the hypotenuse that we are missing the measurement of. Look at this triangle. It's a right triangle. We know the hypotenuse is 20, and we know one of the legs is 15. What we don't know is the other leg, all right? We can still use a squared plus b squared equals c squared, but be careful, the c is always the hypotenuse, so we know the c is 20. The a is 15. We do not know how long that leg is, so we're just calling it x, okay? Leg squared, hypotenuse squared. 15 squared is 225. 20 squared is 400, okay? So now it's algebra. Minus 225 on both sides, right? We're trying to get x by itself. That's 0. So x squared equals 175. We don't want x squared. We only want to know what x is, so we square root both sides. And x, if you do this on a calculator, is rounded to approximately 13.2, okay? So that is how the Pythagorean theorem works to find the missing length of a right triangle. Okay, staying with the triangle topic, let's talk about some other triangle theorems. These don't have to be right triangles. These are for any triangles, all right? First one is the triangle sum theorem, and that says the interior angles, remember the word interior means inside. There are 3 angles inside a triangle, and their measurements will always add up to 180 degrees, okay? So if we know, for example, if we know that angle A is 80 degrees, and we know the measure of angle C is 40 degrees, and we don't know what angle B is, well, 180 minus 80 minus 40 is going to give us 60, which is the measure of angle B, okay? Because 60 plus 40 plus 80 equals 180, okay? They always have to add up to 180. And another useful theorem that goes along with that is called the exterior angle theorem. Exterior means outside, remember? If you took one of the lines, one of the sides of the triangle, and you just extended it out, and you formed an angle on the outside, this is called an exterior angle. And the useful theorem about this says that the measure of that angle is always equal to the sum if you add together the other 2 interior angles, not the one right next to it, but if you add up the other 2, okay? So that angle measurement there is going to equal 60 plus 40. It's going to equal those 2 angles added together. And that makes total sense because, look, this exterior angle plus this 80-degree interior, those 2 angles together fill in the whole side of a line. That should be 180 degrees, right? Well, 100 plus 80, there's our 180 degrees, okay? So it always works. Okay, another triangle theorem that we're going to be using in the coming investigations is called the angle-angle triangle similarity, sometimes written AA for angle-angle triangle similarity. And that one says that if you have 2 triangles and 2 angles in a triangle are congruent, that means they have the same measure as 2 angles in the other triangle, those 2 triangles are similar. They're not congruent, but they're similar. So here's the example. What if we know that angle L is congruent to angle X? They have the same measure. And we know that angle M, so I'm going to put 2 curves, is congruent to angle Y. So 1 curve, those are congruent. 2 curves, those are congruent, okay? So there's 2 angles L and M have the same measures as angles X and Y. What that tells us then is that then triangle LMN, is similar to triangle XYZ. Now, similar means that the triangles are the same shape, but they are not the same size. Okay, congruent, same shape and size. Similar, same shape, different size. So the symbol, notice congruent has the squiggle with an equals, right? Squiggle with an equals, congruent. Similar does not have the equal because it's not the same size, okay? But it's similar, so it has that. Okay, and you can see this triangle is the same triangle, it's just scaled down to a smaller size. Okay, so that is angle-angle similarity. And the last topic that I want to go over for you today is talking about finding the distance between 2 points on an XY coordinate plane. So we have the distance formula. Distance equals x2 minus x1 squared plus y2 minus y1 squared, and you square root the sum. Okay, so that looks complicated, but it isn't. Let's say we start with the 2 points, 3, 4. So 3, 4 is right here. And we want to know how far away is that from the point 12, 10. Okay, so our second point is 12, 10. And we want to know how far apart are those 2 points. Okay, so every point has an x and a y. So we're going to call, this is our first point, so we'll call this x1 and y1. And this is our second point, so we'll call this x2 and y2. And we just plug the numbers in here. So we take the difference in the x's, x minus x. So x2 minus x1, or 12 minus 3. And we're going to square that. Same thing with the y's. You take this y minus this y, 10 minus 4. And you square that. Then we add those two pieces together and we square root the total. 12 minus 3 is 9, square it. 10 minus 4 is 6, square it. Add them and square root. Okay, 9 squared, 81, 6 squared, 36. So we add the 18 and 36 and we square root the total, and that is the square root of 117. Okay? And if we wanted to work that out on a calculator, the square root of 117, I'll do that on my calculator. Square root of 117 is 10.8 approximately. Okay, so you guys, there's another way we can do this, and I'm going to show you because you're familiar with the Pythagorean theorem. So look at, what if that was the distance we were trying to find? What if we did this? Look at, we can draw right along the grid lines in the graph. That's a right angle, and look at what we made. We just made a right triangle. And we can count the units along this side, which is a leg, right? It goes from 3 to 12. So this leg has a length of 9 units. This is the other leg. It goes from a y of 4 to a y of 10. So this is another leg, and it is 6 units long. Well, we can just do that then. We can just say 9 squared plus 6 squared, right? Look at what's happening. 81 plus 36, 117, square root both sides, and look at what we got here. Square root of 117, square root of 117. It is the same calculation. The distance formula is the Pythagorean theorem. It's just written a little bit differently. Okay? And we can do the same thing if we have a point that's in the negative numbers. Don't think we only can work with positives. So what if we have the point 7, 3? 1, 2, 3, 4, 5, 6, 7, 1, 2, 3. So here's the point 7, 3. And what if we want to know the distance between that and the point -5, -4? Okay, so just watch your negatives, but it's exactly the same thing. The distance is x minus x, 7 minus -5. Think about what that means. Squared. Y minus y, 3 minus -4 squared. Okay, so 7 minus -5, that means 7 plus 5, that's 12. 3 minus -4 is positive 7. 12 squared is 144, 7 squared is 49, and we're basically saying what is the square root of 193? Okay? And we could do the same thing by turning it into a right triangle if you wanted to, and I'm not going to do that, but I'm just going to show you if you did. You would see that this length along here was 12 units. This length along here is 7 units. And you could do it with the Pythagorean also, okay? So either way works, and it's up to you how you do it. That's all, guys. Now you're all ready to get started on investigations 3 and 4. Bye.